In this video, I want to talk about group presentations. And to do that, I need to start with generators. Let's let G be a group and A, B, C be three elements in G. Let's let S contain all the possible products of A, B, C and their inverses. So some elements may look like A, B, A, C inverse, or C inverse, A inverse, B, B, C, etc. Then we say S is the subgroup generated by A, B, and C, and this is something that I had defined when I defined cyclic groups as well. But I want to kind of extend this idea. First, there's nothing unique about 3. We can do this for any set of elements in a group. We can form a subgroup containing all possible products of those elements and their inverses. We know that every finite group G is generated by one or more of its elements. And this is pretty clear because I could just let the generating set be all of the elements of G since it is a finite group. However, we do want to restrict that down and try to get the minimal generating group, the smallest number of elements that still generates the entire set. Not only do I want the minimal set of generating elements, I also want a set of equations involving only the generators and their inverses that completely determines the group table. And these are known as defining equations. This set of equations is known as defining equations. So let's look at some examples. Let's consider the group G that consists of the identity, the elements A, B, B squared, AB, and AB squared. So here my generating elements would be A and B. And I also have this set here of defining equations. We have 3 defining equations. And I actually want to build the group table. As we fill this in, we know that EE is going to be E, EA will be A, EB will be B, etc., since E is the identity. As we go through the second row, A times E will be A times A is A squared, which according to our equation is the identity. We then have A times B, which is one of our group elements. A times B squared, which is another group element. We then have A times AB, so that would be A squared B. A squared is the identity, times B would be B. We would then have AB squared, so A squared, once again the identity, times B squared gives me B squared. The next row, B times E will be B. B times A, according to my operations, gives me AB squared. B times B will be B squared. B times B squared is B cubed, which is the identity. We then have B times AB, and for that one I'm going to do some side work. We know that BA is the same thing as AB squared, so this is now AB squared B. We know that B cubed is the identity, so this would result in just an A. The next one, we would have B times AB squared. Once again, I'm going to look at BA and realize that's AB squared B squared. We know that B cubed is the identity, but this is B to the 4th. So we would have 3 gives me the identity and 1 left over, so this is AB. For my next row, B squared times E is B squared. For B squared A, I'm going to go ahead and write it as BBA. We know that BA is the same thing as AB squared. Once again, BA is AB squared, so I have AB squared B squared, which is once again AB. B squared times B is B cubed, which is the identity. B squared times B squared gives me B to the 4th. 3 of those gives me the identity, and then we have 1 left over. We then want to do B squared AB. So we have this BA right here in the center. I'm going to change that to AB squared. We can then see that this is the identity, so I really just have a BA, which is the same thing as AB squared. And then we have B squared A b squared. Once again, this BA in the middle will change to AB squared. This BA will once again turn to AB squared. B to the fourth is the same thing as B, so now I have AB cubed, which is just A. AB times the identity is just AB. The next one would be ABA. Well, we know BA would switch to AB squared. A squared is the identity, so I'm left with just a B squared. AB times B will be AB squared. AB times B squared, well then I have AB cubed, which is the same thing as A. We then have an ABAB. Well, this BA in the middle will change to AB squared. So now I have AB squared, B. We know A squared is the identity and B cubed is the identity, so this would just be the identity. And then the last entry in this row, AB squared. Once again, we have this BA in the middle, so that will change to AB squared. So I have AB squared, B squared. The A's will give me the identity, and B to the fourth gives me B, so this would be a B. For our last row, AB squared times the identity is AB squared. AB squared A. So we have A, BB, A. This here will change to AB squared. This BA will once again turn to AB squared. So now we have the identity times B to the fourth, which is B. AB squared times B, that would be AB cubed, or just A. AB squared times B squared is AB to the fourth, which will be AB. The next one, we have AB squared, so ABB, times AB. Here, we can change that to an AB squared, B. We then have another BA. That will change to AB squared. We can see here is a B cubed, which will just give me the identity. A squared is the identity, so I'm left with B squared. Finally, we have AB squared times AB squared. Here's an BA. I'm going to change that to an AB squared, still times a B squared. This BA will then change into AB squared. This B to the fourth is the same thing as B. So now I have an A squared as the identity and B cubed is the identity, so this gives me the identity. So now I have the group table for this particular group and these defining equations. Let's consider this group G consisting of ABC, AB, AC, BC, ABC in the identity. We know that A squared, B squared, and C squared are all the identity, and it is a commutative group. So this time we're looking at one on 3 generators, A, B, and C. So I want to make this group table. We know the identity times anything is just itself, so I can go ahead and fill in that row pretty easily. Remember, this group is also commutative, so AE will be A squared is the identity. We then have AB, AC. A squared B would give me just B. A squared C gives me a C. We then have A times BC. And A squared BC would give me BC since A squared is the identity. For B times E is B. B times A is AB. B squared is the identity. We then have B times C. B times AB, that's going to be the same thing as AB squared, or just A. BAC is the same as ABC. B squared C will be C. Then we then have B times ABC. That's the same thing as AB squared C, or AC, since B squared is the identity. Next we have C. This will give us C, AC, BC, E, ABC, A, B, and AB. Once again, using the fact that now C squared is the identity. And we can continue this. My next row would be AB, B, A, ABC, E, BC, AC, and C. The next row, AC, C, ABC, A, BC, the identity, AB, and B. Next row, BC, ABC, C, B, AC, AB, the identity, and then A. And then finally we have ABC, BC, AC, AB, C, B, A, and the identity. So this would be my entire group table for this commutative group.